Hello everyone, welcome back to Calculus 1. And this time we continue to work on section 4.6, the limit at infinity. Actually, really, last time we only talked about one basic rule, but anyway, it doesn't cover many cases. It is a limit as x approaching to positive infinity or negative infinity, okay, of any constant over a power function as long as the power is positive, and then the limit is 0. And we did 1, 2, 3 examples. And a limit at infinity could be of anything, at least I want you to know that. And also, I really want to know the limit at infinity could be infinite limit. So like in the case, limit at x approaching to infinity, what would happen? As for a single x, well, it's approaching to infinity. So the limit at infinity, that's an infinite limit. Limit at infinity is infinity. Limit at infinity is infinity. And also can be generalized. Limit at infinity for any power function as long as the power is positive, it is infinity. And also, well, the conclusion are all for power functions. And also sometimes we do consider some function other than power functions. Well, I mean exponential functions and logarithms. So let's take a look at a special case, limit as x approaching to infinity. Limit as x approaching to infinity. For e to the x, it is about 2.7 something. It's the Euler's number. So e raising to the power of 2 to the 3 to the 10 to the 100. They're big, right? They are huge numbers. They are huge numbers. As x approaching to infinity, e to that power, it is huge. It is still approaching to infinity. Well, so the limit is infinity. Okay. Another interesting result I want you to know here is, remember we said that we have a limit at infinity, could be positive infinity or negative infinity. Take your imagination. What do you expect of e to the x, but as x approaching to negative infinity? Well, you will have to keep in mind that this time we are considering e to the power of negative power, which really means we can change this power to positive, put the entire exponential to the denominator. 1 over e to the some positive power. But the power is getting bigger and bigger. It's just like 1 over infinity. So the limit turns out to be 0. Okay. So these are two interesting results. E to the x, I say as we may expect it to the infinity, and x approaching to infinity, e to the x, it is approaching to 0. You may want to remember this. Be very careful. I mean, sometimes on the test, we just maybe do it purposely to trick you, put those two things together to see how you understand the limit at infinity. Okay. And the limit as x approaching to infinity, logarithm log n of x. And the logarithm, believe it or not, logarithm and the exponential function both are increasing functions. And as x approaching to infinity, log n of x, still it is approaching to infinity. And even though limit-wise or in the form of writing, you don't see bigger difference, but I really want you to know the exponential function, it is very important, it is very useful. One special thing about the exponential function, it is the only function such that the derivative is itself. And now the other thing I want you to know, well, the exponential function, it is a function grows at the fastest rate. It's fair to say that. And the logarithm grows. And it's fair to say logarithm, it grows at a very slow rate, not anywhere comparable to the exponential function, but it still grows. So in writing, you don't see the difference, but anyway, in actual calculation, you will see these things are really different. Okay, and then another limit, it may have nothing to do with the limit at infinity. or negative infinity, but anyway, still very interesting. Logarithm. Logarithm, if you know logarithm very well, and you remember this thing here, log of x cannot be negative. So it would not make sense just simply say consider the logarithm of x as x approaching to 0. This notation means x approaching to 0 from right. All the x values are positive. And believe it or not, the limit it is approaching to negative infinity. It is a negative infinite limit. Negative infinite limit. Okay. And how about let's do little more examples. I'm trying to see if I can explain everything. And the first one, it is a limit. All these examples are from the textbook. This is from the book 4.25, part 8. We are considering the limit as x approaching to infinity of a rational function, right? A rational function, it is in the form of a polynomial divided by a polynomial. And also interesting enough, in this case, the degree of the numerator and the degree of the denominator is the same. They are the same. So what I did here is to consider this limit. I divide the numerator by x and the denominator by x. I do the same thing for the numerator and the denominator. To manipulate a fraction, you always do the same thing for numerator and the denominator. Okay, and then what I figured out here is, well, as x approaching to infinity, now this is 1 over x, it is approaching to 0. 5 over x, it is approaching to 0 too. So later, this turns out to be 3 over 2. And similarly, we can consider the situation x approaching to infinity. Indeed, I said I really should combine these two together. But anyway, just make sure these are really two different situations, two different limits, but they turn out to be the same value. Okay, they turn out to be the same value. And this indeed, it is the case. I want you to know it is the case for the limit of a rational function such that the degree of the numerator and the degree of the denominator are the same. And indeed, it could be of any number. It could be of any number. And the next case, really still it is the limit of a rational function such that the degree of the numerator, it is less than the degree of the denominator. And in such a case, what I did here is I have two limits combined together. Still make sure you do understand, I really consider those two, these are two different limits. But anyway, somewhat they are taking the same limits, same limit here, okay. So I combine the writing part together. I divide the numerator by x cubed. This x cubed, it is from the term highest power, the term with the highest power in the denominator. Okay, and then each term of numerator divided by x cubed, which turns to be 3 over x plus 2 over x squared. Each term of the denominator divided by x cubed, which turns out to be 4 minus 5 over x squared plus 7x cubed. Remember those basic limit rules, and we can add limits, we can subtract limits, we can divide limits, we can multiply limits. So using those properties, we figured out the limit here, there, these two terms on the top. As for the numerator, they are 0. And the limits from the term for the terms of the denominator, this is 4 states. This is 0, this is 0. Because the numerator is 0, denominator is a fixed number. So overall, the limit is 0. There are two limits, but anyway, in either way, the limit it is just 0. Okay. And also, as I'm saying, be a little more sensitive. I'm saying this is the case such that the degree of numerator is less than that of the denominator. Okay. Indeed, it is always the case when you have the limit at infinity such that the degree of numerator is less than the degree of denominator, it is always 0. And then when you have the case degree of the numerator equals to the degree of the denominator, then the limit really would be the same as the ratio of the leading coefficients of the numerator and the denominator. If it is 3x squared, that tends to be 2x squared. This is still 3 over 2. If it is 3x cubed, 2x cubed, this is still 3 over 2. That's all I'm saying. And then we do have one more case to consider the limit at infinity. And it is a case such that the degree of the numerator it is bigger than the degree of the denominator. So in this case, what I did here is I'm still doing the same thing for numerator and denominator. I divide the numerator by the term x, which really is the leading term from the denominator, and denominator divided by x. And then I worked with the division for the numerator. Okay, 3x plus 4. Division for the denominator tends to be 1 plus 2 over x. As x approaching to infinity, what we are having here is well, this as x approaching to infinity, 2 over x, it is approaching to 0. So this part should be true because x approaching to infinity, the numerator it is approaching to infinity. So it is infinity over 1. But anyway, I should correct myself. Maybe it's better to separate these as two limits. But anyway, I'm trying, well, cannot make too big a change for now. Maybe I'll change it later. But anyway, I think still this should make sense. You may want to know, as x approaching to negative infinity, the limit would be negative infinity. So this now it is correct. Really, there are two limit problems. Should be separated. But anyway, I hope you understand. Because plus minus really means there are two limits. And at the infinity, it is positive infinity. It's positive infinity. At the negative infinity, it is negative infinity here. Okay, negative infinity, negative infinity. So that is about situation limit at infinity. Maybe let's just finish one more example to see if we can handle the case quickly. Do we need, I guess maybe just, anyway, let's take a break first before I make this video too long. Thank you for watching. I'll see you next time.